So I am very happy to see so many people in India interested in listening to homogenization talks. Okay, so my talk is about what is known as H measures. The talk is about H measures, and the authors are well known: Professor Luc Tartar, Patrick Gerard, and so on. So in the context of homogenization, there is one celebrated theorem due to Murat Tartar and Yuri Sherkayev. It's about characterizing mixtures of composite materials, how to characterize them when in the mixing process there are two materials which are participating. So there are several proofs about this result, and so there is one proof using H measures. So I will try to explain what I mean by these things. And my interest in H measures came about because we extended that method of estimation from homogenized matrices, namely A star, to some new object, macro coefficients, which we introduced, which extends this homogenized matrix. So it is by means of this extended limit, we could solve more, let us say, there is a rich class of optimal design problem which we can solve. Okay, I'm not going into those applications. Here, you can call this lecture as a preparatory material to, but I will give you references if you like. So these are the authors, okay, especially Tartar. Because Gerard approach is more sophisticated. It required several developments in theory of pseudo-differential operators, which I am not going to do. Okay, whereas the approach of Tartar is a down to earth and real analysis, measure theory, and things like that, functional analysis. So we can follow that. So there is a well-known book by Tartar on theory of homogenization, general theory of homogenization. General theory of homogenization, where you can find all these materials. Okay, so I will not get into, because the mixed nature of the audience, I will not get into too much technicality. Anyway, the reference is there where the proof is presented in all its glory regarding H measures. Okay, so the problem is, of course, you have a sequence converging weakly to 0 on any compact set, So the motivating question has been always the following one. Right? This is the fundamental question. And in the context of homogenization, we know the culprits, okay? So the culprits, that means obstacle to this strong convergence, are oscillations and concentration. That is the problem. So you have to somehow describe them and then try to see what your equation means for these things, whether they eliminate these things or in spite of these equations, they still continue to persist with some restrictions. So all those questions to be analyzed. So there are various tools. So for instance, defect measure. Was introduced by and exploited by Lyons in fluid flow problems and in the theory of concentration compactness by Pierre-Louis Lyons. So this is just U. So U epsilon is a function of x is in Rn. So you take a square. So this is on any compact set, it's bounded density L1, bounded in L1. So it will converge to some measure nu. So this is called defect measure. So nu is a measure in Rn, radon measure. And of course, it's a non-negative measure because these guys are non-negative density. So if you like, so sometimes I write like this, sometimes I can put a dx there. So I am looking at U epsilon x square as the density with respect to Lebesgue measure, and it is bounded on compact sets. And for a subsequence, we know that because this space is it's a dual space, C0 star. So we can extract a subsequence so that this happens. Now, nu equal to 0, if and only if there are no oscillation and concentration. So we have strong convergence. No oscillation, no concentration. Okay? And as I told you, this fact has been exploited in nonlinear problems beautifully by Lyons and Lyons-Diperna in several examples. Now, this measure, which is in the physical space, Rn of x is physical space or configuration space, as you may like to call it, it's not good enough. It's not good enough. This is a culture of thinking from harmonic analysis earlier. So nu is not good enough to feel the real impact of, when you impose differential constraints. U epsilons are, you can imagine it is an approximation to your original PDE, which you want to solve. And so PDE, as you know, is of course in X space. But then because of the differential operator in the Fourier transform, even in a constant coefficient case, you have a psi variable. So it's a mixture of all these things. You have a variable differential operator, variable coefficient differential operator. Variable coefficients, of course, is in X. You are localizing in X. But on the other hand, because of the differential operator, there is automatically, in some implicit form, psi variable, that a Fourier variable is sitting there, right? So this is not good enough. We want a tool in X psi space. So if you call it this configuration space, this is called a phase space. So we are in Rn, X, or in omega, if you like. But here you have or n psi. So we are looking into, so for people who are geometrically oriented, this is the so-called cotangent space. So it's automatically there implicitly. So there is this culture of extending some objects in X space, which lives in X space, to this cotangent space, this phase space. So this is an old story. This is an old story. And of course, several people have worked on that. I can only cite some of the things which I have read. So, especially in the context of PDE, these people, Joe Keller and Romander, as you know, that he has written 4 volumes of books on partial differential operator. How to exploit this idea of extending to phase space. How do you develop the theory geometrically, analytically, and applications. Okay, so you have a lot of things. But what is the feature which is extended to phase space? And that is singularity or regularity. Not all properties from X space can be extended to this phase space. So the technical term is if you have a property which can be localized in X space, then you say simply localizable property. That is in X space. So it's simply, if you have a distribution, it can be localized by multiplying by a cutoff function. We all know that. And still you get a distribution. C infinity function. You multiply by a cutoff function, smooth function, you get again a C infinity function, again, in fact, with the compact support. So they are all localizable properties. And here, I am talking about micro-localizable. So this is the technical term, okay? Now, their basic observation is that singularity can be micro-localized, okay? And that gave rise to the concept of wavefront set, okay? Wavefront set of a distribution. So this is wavefront. Of a distribution. So this is an object in Xi space. In fact, it depends only on the directions, not on the modulus of psi, only the direction of psi. Okay, something happens. Something happens associated with the distribution. So, roughly speaking, you position yourself at a point, x0, and then look at a cone of positive angle. Here, the Fourier transform of a localized version of t at that point, x0, is rapidly decreasing. Okay, so we are not going to use it, so it's just a motivation. So support of t is in omega or in Rn of x. It's a closed subset of that. And similarly, singular, because we are talking about regularity and singularity, C infinity singularity. So this is again in x. So this statement is something like that. Okay, it's a tool in X. So this is an object in X space. Now we want to extend that following. So I want to replace this singularity, regularity with non-compactness, compactness. So fortunately, this is one of the basic ideas of Tartar, that compactness, non-compactness can be micro-localized. Okay, so this is the basic idea behind the works of Tartar and Gerard in this area. Okay, so with that in mind, so the H measure is going to be, here you see WFT. So this is in Rn Sn minus 1 psi. I can project, right? Projection, X projection. So I take a point xi and I project to X. So just I look at the base point. So over that, the entire cotangent space is standing. I look at the base point, and here I come back to Rn. So under that projection, if you look at WFT, wavefront set of T, it and it is onto. So in other words, this is a set in phase space, and when I project, it maps into singular support. Singular support, as you know, is set of all points where the distribution is not given by a C infinity function in any neighborhood, So that is, it's just extension of this, right? I mean, this, you look at whether T vanishes on an open set or not. Here, you replace that statement by asking whether T is C infinity in a neighborhood, at a point. So this captures all the C infinity singularities, and this map is onto. So in other words, so this is what one calls micro-localization. This is usual localization, localized object in X, and this is micro-localization because at each point in X, there is a fiber, there is a set of psi directions standing over that base point X. And what does it do? They are responsible for creating the singularity at the base point, which you don't see in the normal description of objects in the physical space. But it is there. It is there. And through differential constraints, when we impose a differential equation, we are trying to restrict the number of bad psi creating singularity. That is a restriction we impose, right? That is what I motivated through the Fourier analysis. And so, you see the differential constraint tries to eliminate certain bad psi. That's the basic idea. If you do not look for this phase space tool, you completely miss that information. So this is important. That is the main motivation for looking for objects in the phase space. Because PDE forces you to do that. And that is why nu is not sufficient. You have to go further. So we will introduce this H measure, which is a measure like that on this phase space. Actually, it is not a phase space, though I call it colloquially phase space. It is what is known as unit cotangent bundle, because these are all unit vectors. So it is only a measure on that bundle. Okay, so let me complete it. So you have projection. So you have a H measure. When you project under the same map, you get defect measure. Okay? So projection of mu is equal to nu. Similarly, exactly like that. Exactly like that. Okay. Now, given all these things, now let us start. So I am given u epsilon, which converges to 0 in L2 log Rn. So that means I take any cutoff Cc. Okay. With any cutoff, I have this. I remove this log and I introduce a cutoff. Okay. Now I say, so these are some of the elementary exercises which I can leave it for the students, but of course I will give you some hints. You can you can work it out, right? So phi u epsilon hat psi. Okay, this converges to L2 log Rn, of course, with respect to psi variable. That is what I wrote. Okay. So with respect to psi. So what is Fourier transform? You know the definition. Okay, yeah. L2 log, I mean, you want a definition. Yeah, 0. I wanted to put the full arrow. That is the, if that is the mistake, yeah, I agree. I wanted to write the full arrow. So, in other words, this weak convergence gives rise to this strong convergence, essentially because, you can apply dominated convergence theorem. So that is the hint for the students. Apply dominated convergence theorem. So I have to prove okay, this is what I have to prove, and dominated convergence theorem. So I need pointwise convergence, which is true because this is localized. It's actually over the support of phi, which has compact support, and this is localized. And so, but this is a fixed function, which is on compact set is in L2. Generally, it is in L infinity, but on compact set, it is in L2, and there is a convergence to 0. Convergence to 0. So pointwise convergence follows, and that it is bounded, L infinity bounded, follows from Riemann-Lebesgue. You must have done several exercises like that, Riemann-Lebesgue lemma. So this is a simple exercise. You apply this. I have given you enough hints. Okay, so now you see the situation is that on any finite part of the domain, there is no energy because we have strong convergence on any ball. It goes to 0. Norm converges. So where is the energy? Why there is a problem with the strong convergence? The thing is that there can be concentration at infinity. Because when you look at various criteria of compactness in L2, there is a possibility of energy going towards infinity. So here the energy, so this L2 norm I call sometimes energy because it's a quadratic quantity, okay? So the compactness can fail at infinity. So the idea of Tartar and other people is that, so what does it mean? It means that when psi is large, you don't have that strong convergence. And when psi is large, people say it's birth of small scales. Okay, you have to get used to this notion because we are dealing with a multi-scale workshop. So small scales are generated by this sequence automatically because only when psi goes to infinity, large wave number, there is a problem, okay? There is a problem. So small scales are generated there in the sequence, and one can say that that is, the small scales can be the source of oscillations and concentration. Okay, that is what I have written here. Okay, so whatever I have written, that is the problem, yeah.
Equivalent at high frequency numbers in a way because high frequency numbers you deal with very highly oscillating waves
Correct.
the material.
Correct.
Therefore, small scales get a meaning.
Yeah. So more simply, since you raised L2, okay? It's convergence as n goes to infinity. I have changed, okay, you call it x by epsilon. So it goes to 0. So this can be your u epsilon. But then you take this kind of operation. We know that it's a simple exercise if you do not know already. So this is in d prime. Okay, L infinity weak star if you like. So this is the effect. So as epsilon goes to 0, there are small scales. You see, sine is a periodic function of period 2 pi. By putting a epsilon in the denominator, I make it 2 pi by epsilon. 2 pi multiplied by epsilon. So this is has periodic oscillations. Period is 2 pi epsilon. As epsilon goes to 0, you see, plenty of waves. And that is what I call small scale generation. And the effect of that, when you compute energy type quantity, it does not converge to 0, it converges to half. This is the effect. In fact, if you can understand this example, okay, the general theory, of course, includes this understanding of this example. Okay, so this is the effect of this oscillation in this example. Now, okay, so the idea of Tartar is to micro-localize this. Having come up to this, now what it does is that okay, let me explain. So I already drew a figure like this, but here I don't want to miss the point. Okay, so what is psi? Psi is a test function in fact, a continuous function on the unit sphere. That means it is a function of directions. So psi by mod psi for every psi in Rn, okay, 0 is excluded and it doesn't matter, it's a measure 0. So you have psi, so it is, you take the unit sphere in Rn, so this is your psi direction, so this is your psi by mod psi. So this is Sn minus 1. And you take another one, eta by mod eta. So you have all the unit directions. And psi is a continuous function over here on a compact circle. So in other words, psi can have, for instance, support here, for instance. And here it is 0. Psi is arbitrary. Psi is arbitrary. So in that sense, you see, by choosing a particular direction and by choosing psi localized in that direction, I can localize that energy in psi space. This is what is known as micro-localization. Because we have already localized in X space by multiplying by this phi, it's already there. Now I am localizing in the space of directions. So this is micro-localization. In other words, he wants to look at the behavior of this energy escaping to infinity direction-wise. Direction-wise. Okay, so you have this. Now, so what is the proof of this? What is the next result here one can prove is the following. Okay, so in some sense, by taking the support of psi is small, you are looking at the energy along that direction, So what do you expect is a measure, radon measure, mu phi, depending on phi, because this is bounded in L1 with the square there. So you expect something like that. Now, the next question is, what is the dependence of this radon measure on phi? So he proves that this is like that. Phi is a function of x, and psi is a function of that direction. Okay, so this is that notation. It's a function of x and psi. Psi is in Rn, or Sn minus 1. Okay, so this is called H measure. So this is the idea. Now several things to be done. Okay, you can first of all localize like this by taking two functions when phi1 equal to phi2, you get that expression. Okay, so this is a simple. Now phi1, phi2 are functions of x. So this is x localization, and this is function on the unit sphere. Now we want to say, because we want a compactness theorem, so we want to say that there exists a subsequence such that this limit exists. That subsequence is independent of all the test functions. So the same subsequence works for all the things, all these. And the limit is, at the limit you have a radon measure, which is a measure on x space Rnx cross Sn minus 1, mu. And this limit is equal to that. That's a H measure theorem, fundamental theorem. Okay. Now, so you can expect the only point here is perhaps the dependence of phi. You have to remember that when I have two functions. So when I take phi1 and phi2, I get that, and so I have to put square here, sorry. Square. Because in two places, phi occurs quadratically. Phi occurs quadratically here. So I cannot expect linear dependence at the end. Okay, so this is the content of, yeah. Of course. So if you have this, so that is the limit for that expression. So naturally, this one I expect phi1, phi2 bar, of course, in x, and this is with respect to psi variable. Correct, thanks. Okay. Now, this is the idea of micro-localization. This is the idea of micro-localization, of non-compactness, by introducing, so for people who have worked on two-scale convergence or even weak convergence, we are used to taking test functions of different classes of test functions. Psi of x, psi of x by epsilon, and so on and so forth. But here, it's different. It's different. You have to go to phase space and do this. And all these oscillations, concentrations are captured by this guy in the phase space. Okay, I will come to the interpretation part later. First, we have to show something here. Okay, so this is the statement. Now, how do you prove this? So first of all, you have to extract a subsequence independent of the test function. This is in our culture, right? From the beginning. Arzila, Ascoli, things like that. So that is one of the first places where we indeed extracted the converging subsequence in Arzila, Ascoli. So what do you need? We need two ingredients. One is that boundedness of the sequence, and second is that separability of the underlying space. If you have these two things, you can carry out this so-called cantor diagonalization process. So that is the only process we know. So we can do that. And we have all those things. So the underlying space is these things which are separable. So we can take a dense countable set, and then along for each element in that sequence, you extract a subsequence, and then take the diagonal sequence afterwards. And the boundedness independent of epsilon, of course, we have u epsilon, in fact, converges to 0 in L2 loc. So we have boundedness also, we have localized. All those things. So boundedness and separability. We have. So this convergence to 0 might disturb some people. Why this? Of course, technically, as I was shown there, nothing happens on the finite part of the space, psi space. Everything happens, if something fails, it's only at infinity, small scale generation, only at infinity. Okay? So there we used u epsilon converges to 0 weakly in L2 loc. We have used that. Now, so here I have a glass. You see, the water is still. So the macro limit is 0. Velocity of water molecules, macro movement is nothing, it's at rest. But then actually it is not at rest, right? It is not at rest. And there is energy concentrated at the molecular level. And there you see, because of that energy changing because of various collisions of water molecules. And the collisions can be binary between two molecules, or it can be ternary or higher order collisions, though higher order collisions are rare, agreed. So, what we are trying to do is to capture the energy in binary collisions, hence this product. Okay, and as psi happens only at infinity, that means only the highest energy binary collisions. Highest energy. So, very strong collisions. The, let's say, less energetic binary collisions, well, I mean, it's a limit process. So, you have to take limit in the, that psi going to infinity. That means the smallest scales possible. Psi large enough is not good enough. You have to really let the psi to infinity. That means a really large energetic binary collisions you are looking at. You may think that there is whole culture of Boltzmann equation and things like that. But Boltzmann equation, as you know, assumes various hypotheses, especially molecular chaos, which is may not be acceptable by other experts. So there is a problem. Whereas this one is a mathematical theory. There is no question of ifs and buts. There is no hypothesis. So what I want to stress upon is that u epsilon going to 0, the limit, a weak limit 0, corresponds to such situations. That's what I'm saying. And the H measure captures the energy, it's an analogy in these strongly energetic binary collisions. If you look at ternary collisions and so on and so forth, problem is open. Okay, problem is open. And similarly, just to hold on. Similarly, you shake the thing so that binary collisions are affected. High energy binary collisions are affected. Then also, problem is open. Okay. Tartar does that too. The thing is that time scales differently. That's the main aspect. New aspect, if you like. So, if it is S scale, S square there. So, modulo that, the entire theory goes through. Okay. So, that will be necessary for parabolic problems, for instance. And when it comes to hyperbolic problem, it's the same as in here, both psi and x and t space. It's the same scaling. That's why H measure describes very well the propagation governed by the wave equation. No problem. It overcomes the problem of caustics, and it gives very much how the energy density propagates in x and space in caustics or even beyond. The whole approximation is valid. The only thing is that it requires some smoothness. I will come to that. Smoothness of the coefficients. That is where we have worked on. Okay, we will come to that. Yes.
Slightly related to the order of the differential operator.
No, it is the scaling properties of the differential.
Scaling comes because of the.
Yes, that is true. Yes, that is true. Yes. Okay. So that is so you need not be puzzled by this because it is an underlying physical assumption. If you try to alter the binary collisions by introducing some energy from outside, then the whole picture will change. Whole picture will change, and nobody knows the situation. Okay. Okay. So I declare that I have extracted subsequence independent of the test functions. Test function. Okay. Now. So, this limit exists, and I have to show that it depends only on phi1, phi2 bar, that combination, product. Whereas here, it's not obvious, right? It is not obvious. V1, V2 occurred in two different places. That combination is not there. So this is the important point proved by Tatar. So the question is, why the limit depends only on this combination? Okay, the linear dependence on psi is reflected here. That's not a problem, but the problem is with the phi1, phi2. Now, there is a nice argument. We have to introduce operators. This is something which we are not used to, right? I mean, we discussed during breakfast algebra of operators and things like that. You see, normally if the operator is given by a multiplication operator, multiplication by a function, then we deal with the multiplication function. We don't deal with the operators. Here, of course, we are dealing with the multiplication functions everywhere. But then we have to look at the corresponding operators. Okay, so some operators, multiplication operators. Why people do not look at operators corresponding to functions? Because there is this disturbing algebraic property, namely non-commutativity, which might create problems. Okay, this is the basic algebra problem, algebraic problem, which might trouble. Now, this is what one has to overcome. So, let us see. So, if you have a B in C0 Rn, that is continuous function vanishing at infinity. So this is the class and then M, B, V to B of x, V of x. So this is L2 Rn to L2 Rn. In fact, you can take B is in L infinity. B is in L infinity. So you take B, you take B, B. This is your MB. Multiplication by. You can, it's a old, I mean, it's a localization. It's a localization operator. Localization in X space, X space. Now, considering multiplication like this by MB operators, okay, this is the a culture which exists since a long time. Perhaps the importance of that came about when quantum mechanics was born. Okay, Heisenberg characterization of quantum mechanical phenomena. One of the important things he discovered that at the quantum level, namely small scales, nature is non-commutative. Whether you like. In general, things do not commute. So, observables are considered as measurable quantities which are modeled by self-adjoint operators, and self-adjoint operators are not commutative. Even two matrices in general do not commute. So, whereas if you look at inside function class, of course they are commutative. So, since we are dealing with the small scales, it's not a surprise that Tatar goes into these operators. Okay, this is the multiplication operator in X space. Similarly, multiplication in psi space. So you take A psi in L infinity. And this is multiplication in the Fourier space. So L2 Rn to L2 Rn. So okay, B hat psi so this is P A operator P. So this is localization in X space, this is localization in psi space. So since I pronounced quantum mechanics, this is position operator, generalized position operator. This is generalized momentum operator. Okay. So for people who like no, I am just trying to motivate what Tartar thought about it. Of course, he doesn't explain all these things, but then it is implicit for, yeah. Where? No, I need this. It's only, it's, yeah. Yes, only. Yeah. So, I mean, sorry? These are bounded operators. Bounded operators. In fact, the norm of is equal to norm of B in L infinity. Right? This is a well-known fact. And similarly, norm of the momentum operator. So this is the linear space of operators. So since you asked the question, let me check. So you take a Fourier transform of P A V is equal to A Fourier transform of V. This is what he writes. So it's okay. Okay. Since Fourier transformation is a unitary map, you get this equality also. So in fact, you can write PA, you see this hat. So if you want just to PA explicitly in terms of operators, it's like that. So in other words, F PA is equal to M A F. So you take any V like this. So PA V hat, this is the Fourier transformation, is V hat multiplied by A. That's the thing, okay? So this is the basic relation. And because F is unitary, so it does not alter the norm, so you get back the same norm. That's why you get L infinity over here. Okay, now why he introduces all these things? Because I told you, this is the basic question. This is the basic question. He wants to commute. If you commute, things are easy. Okay, let us see. Now, I want to write the following. That phi, okay, we have f for Fourier transformation. Somebody asked something?
There is some notational problem.
Notation problem.
V hat is going to A xi V hat,
Yeah.
and then you are applying TA on V.
Yeah.
Some sort of P and V hat.
Okay, I mean, see, I am working.
Yeah, that's what I'm saying. There's some notational problem. That line. Yeah.
Well, I mean, okay, here it's actually MA, okay, at that notation. It's actually MA. And P is defined this way. And the relation between these two is this, okay?
That's fine.
It's,
Then PA of P is defined via its Fourier transform.
Yeah, so
That is not
earlier when you
now the notation is clear, right?
now it understands.
Ah, okay, fine. Yes, thanks for pointing out that, yes. Yeah. So, I rewrite my quantities like this. You have to get used to this. It's not really complicated. I told you it's micro-localization. So you are used to U, V bar, that kind of product integral. That is in Plancherel theorem, Parseval's equality, all those things. Now, in addition to that, you have this factor. So you have to keep track of that. So you have to get used to it, okay? Now, this can be written as F phi m phi 1 u epsilon. Okay? Of course, psi is there. F m phi 2 u epsilon. And then psi now I want to write further. P psi P, the momentum operator. Because it is acting on Fourier transform. Right? I want to take it this along with this factor here. So what do we have? P psi m p1 u epsilon, okay, hat, okay, F. And then F so when you have see what I am writing there is this relation. So F P A V is equal to A F V. So if you have a function of psi multiplying, I can put inside this and take F. This is precisely that, the right-hand side. And this one I keep as such, no change. Now, when you do this is a clever trick. When you do this in terms of operators, okay, you can write Parseval or Plancherel. P psi m phi 1 u epsilon x. No psi, x. M phi 2 u epsilon x dx. Okay. Now, so this is the inner product between this function and that L2 inner product. And I want to take this m phi 2 over here. So what do you get? M phi 2 star, which is m phi 2 bar. M phi 2 bar. P psi m phi 1 u epsilon. So all these things, okay? This operator acting on u at x. And then u epsilon x bar dx. Now, I want to see phi 1, phi 2 bar. Okay, phi 2 bar is here. But the phi 1, so on the right hand side here, I have m of phi 1, phi 2 bar. Multiplication by this combination. M of phi 1, phi 2 bar. Whereas here, m phi 1, m phi 2 bar separately. And this guy is in the middle. So this is spoiling the party. So we have to worry about this guy, commutator. So m phi 2 bar p psi. So this is algebraic object. We would like to have this 0. We like to have this 0. Suppose it is 0. We don't know. Suppose they are commutative. Suppose I can interchange this operator with that. Any position operator with any momentum operator. This is the basic principle of Heisenberg, right? In general, they do not commute. Suppose they commute. In that case, I write this p psi m phi 2 bar. Now m phi 2 position operators among themselves commute. No problem. So m phi 2 bar, m phi 1 is equal to, afterwards what happens is that I use this. M phi 1, m phi 2 bar, both are equal to m phi 1, phi 2 bar. And we are done. So that combination appears. And nothing else. No independent phi 1, no independent phi 2 appearance. Only this combination appears, hence the question is answered. So all these things on this important, but we know that these things are not commutative, okay? So, I told you, if it were commutative, we will have this answer independent of, depending only on this combination at every epsilon level, which is unreasonable to expect, right? It's unreasonable to expect at each epsilon level. We expect this commutation only at the limit as epsilon goes to 0. Okay. So something happens at epsilon equal to 0. What is that? So this commutator, okay, so let me write. So, so if you want, this is intrusion. This is also motivation. So I will write p psi, what I want, okay? I commute these two from here, u epsilon x, u epsilon x bar dx plus, because I have committed an error. I committed a mistake, which is this. Namely, I add and subtract something, and that gives rise to this commutator. This is the so-called commutator. which is by definition m phi 2 bar p psi minus p psi m phi 2 bar. They are all bounded operators defined all over Rn, and so we have this. So this is the definition, this square bracket notation. Now, people have been coming across this object in several occasions. In PDE also, in the regularity theory, commutator estimates is something. It's something celebrated. Okay, it's a lot of people have worked because there are cancellations in this minus sign. There are some cancellation, beautiful cancellation. The typical example, one of the first exercises I did, if you take a vector field, two vector fields with, of course, variable coefficients, okay, two vector fields with variable coefficients, and they are all first order operators. You look at the commutator. You can look at the commutator of two operators. So when you compose, you see, two operators, you get in general an operator of order 2. But because this is of order 2, in the case of vector field, this is an operator of order 2 with a minus sign. The second order term from one term once cancels with the second order terms in the next one, and you get a beautiful first order operator which corresponds to another vector field. So this is an exercise. So commutator surprisingly has many beautiful properties, including some of the recent things in control theory and so on and so forth, geometrical control theory. Okay, and Hormander, he uses it very beautifully. Okay, commutator estimates, and of course its importance in quantum mechanics already was felt by the various philosophies of Heisenberg. And the operator algebra theory also, they deal with this object. Okay, now what is its relevance in our context? Okay, because of that cancellation, this is more regular than the individual operators participating in that. So how does it that philosophy translate into in our? So in our case, commutator is compact. It's a compact, it's not arbitrary bounded operator, but it's a compact operator. That means weakly convergent sequences will converge strongly. Okay, so when you take the limit, this is the extra error term, but that is compact. That is compact. And these guys converge weakly. So this one acting on that will converge strongly, and this is weakly convergence. So this whole thing will converge to 0. So this error term, because of this property, will converge to 0. So you call this as number 1, and this is number 2. So the term 2 will converge to 0 as epsilon goes to 0. Because of this. The compact operators are in some sense small operators in the compactness theory, okay, negligible operators. In the singularity theory, again, the Hormander's theory, again, commutators played a role. They give rise to more regular terms. So at the leading order singularity, they don't count. But then you have to prove the corresponding commutator estimates. There is, of course, a lot of geometrical things also. It is a non-commutative Poisson manifold and whatever. Okay. So you have to prove this. How much time? Oh, I have 20 minutes. Okay. So this is the main, okay, let's say this is the main thing to be proved in the Tata. All other things are in some sense more elementary than this. Okay, this is the non-trivial thing. And when is the commutator of position and momentum operators compact? Okay, this is the Under what conditions? This guy. Okay, generally I state. This is the compact. So here is a surprise, and it may not be liked by homogenizers, right? You can take A to be L infinity, right? A to be L infinity. B so given the fact that we are dealing with the microstructures, we would like to take the coefficients to be as rough as possible, actually. So in particular, for composite material, this is the relevant class, L infinity. But it's not true that if you take B in L infinity, A is in L infinity, the commutator need not be compact. In that case, this argument fails, and several other things fail. For instance, can you admit a phi1, phi2 instead of continuous function? Can you take it in L infinity? You can ask that question, because after all, it is X localization. You cannot do that, because in that case, the space is no more separable, and extracting a subsequence, that procedure, cantor diagonalization process fails. Okay? You can do with the filters. Okay, that's a different thing. That's a different story. Okay, so at least there are two obstacles for taking larger test functions, larger in X space. One is that separability, or rather non-separability. Another one is that this compactness fails because, so answer is no. And Uchiyama, he proves that a necessary condition for this commutator to be compact, so we are not going to touch that because it is more into harmonic analysis on B. So B must be in the space VMO, vanishing mean oscillation. So there is this bounded mean oscillation space by Fridtjohn, and this is introduced by Fridtjohn and later studied by John Nirenberg. Actually, he came across this space in his study on elastic strain, elastic stress. Okay, so it's one of the nice instances where applied mathematics really gave rise to various developments in harmonic analysis. Okay, VMO is just you take all those functions with which vanish at infinity, take the closure. This is the Banach space. So vanishing mean oscillation. Okay, there is a paper by Uchiyama. If you want, you can. So it is with just L infinity function, you cannot hope to. There is no compactness. So once the compactness fails, I don't know how to carry on. Okay, so you have, so in our context, what happens? So we are taking, so let me announce that. So lemma, commutator lemma. So we are going to take B in C Rn vanishing at infinity, and A in L infinity. So this is, I told you, this class is sitting right there. So everything is okay with that class. Then this guy, PA, MB, this commutator is compact. Proof is technical. Well, I mean, it's not very difficult, but technical, since it is presented in Tatar's book. Okay, if time permits, I will do, but since we have taken phi1, phi2 continuous function with the compact support, and we have taken psi in C n minus 1, continuous function of the unit sphere. These hypotheses are satisfied in our case. So we can commute. So we can neglect the effect of this term because this will give rise to 0. So at the limit, this guy is equal to that guy. Now, once you have that, I already told you that we are through. We are through. So we have that, and so limit of epsilon going to 0 is of our, okay, phi 1 u epsilon hat psi, phi 2 u epsilon hat psi d psi is equal to limit of that guy. P psi m phi 2 bar m phi 1 u epsilon bar dx. Now, so this is, I continue. So p psi, I phi 2 bar dx. So I can go to Fourier transform, huh? No problem. But anyway, the limit is, so in particular here, limit is, depends only on phi 1, phi 2 bar. That's the main thing. Now, next question is, I have to show that limit is a measure. Limit is a measure. So, we know that from theory of distributions that any non-negative distribution is given by a Redon measure. We know that. So that is what we want to see. Okay. So for that, so why the limit is given by a measure? So the limit is like this, right? So for the moment, it is a distribution. Okay, distribution. Why this limit is given by a measure. And okay, first of all, you have the limit. You can define like this. limit epsilon going to 0, phi u epsilon, sorry, I take phi 1, phi 2 equal to phi. So the limit exists and depends only on mod phi square here, mod phi square. Now you choose any phi arbitrary. And psi non-negative. Psi non-negative. Because it's only mod phi square which appears in the limit, that is what we have proved. It's always non-negative. But then if you look at this, with this condition, you say this is equal to so it is always non-negative. For each epsilon, this is non-negative. So the limit is non-negative. So the non-negativity of the limiting object is easy because of this dependence only on the product. That's why I could write this. I could write this phi square here and argue like this. So the limit would be something like this. And this is arbitrary, and this is any arbitrary non-negative test function, and the limit is, the value is non-negative, so we are done. So what we have done is we have analyzed scalar sequences. It's important, scalar sequences. If you go to vector sequences, that u epsilon is a vector with some finitely many components, and you can take any two components and then argue same way. You can introduce phi 1 as a cutoff function with one component and phi 2 another component, and again you can pass to the limit and you can do the same thing. Only thing is that you will get a signed measure. You will get a signed measure. So I just wanted to project something. Is there any projector or something? Yeah, but I have. Yeah. Oh, here it is. Okay, that's what I. Okay. No, this is not. No, this will be shown. This is not the right file.
Look here.
Yeah.
Here, which one? This one?
Maybe here. I double click.
Yes.
Yeah.
Yes. No, it's
Open that. Open. Let us see. I forgot which one where I put.
this one.
What happened?
Not this.
Okay.
This one.
Yeah.
Okay. There are 7 pages.
Yeah, I know.
Okay.
So this one is. So this is the theorem which we discussed for the last 1.5 hours or so. So this is the restating what I. Okay. Is it working or not? Working? Oh, switched off. Okay, now it's working. So this is the thing. So you have any sequence which converges to 0 in L2 log, you can have omega X space, no problem. And the result is that H measure, which is a measure in the phase space, omega cross Sn minus 1. So this is the X variable and this is the psi variable. M is the measure space, Redon measure space. And it is a non-negative measure, and we have extracted a subsequence independent of the test function. So the statement is valid for all test functions, and this is the statement. This is the statement. And in particular, you notice that this right side depends only on this combination. That's the crucial fact. That's the crucial fact. Now, what is the corresponding? Is it? Yeah, but it's not moving. It's not.
You not put the text. You not kept. Yeah. Keep that.
Okay.
You are not given information to see from there.
Yes, of course. Okay. Now it opens. Where is that? Where is that vector valued version? No. Next page. Next. That is the last. Then I am in trouble. What is this? Here. Okay. So there is one additional thing. So you look at the same combination, similar combination. Only thing is U epsilon is now a vector with some p components, let us say, p components. U epsilon 1, U epsilon 2, U epsilon p. And each one of them converges to 0 locally in this L2 weak topology. Of course, as before, there is a subsequence because we are dealing with some finitely many indices and measure. What is now the measure? Because we are taking Uj, Uk, right? You can fix any two indices and you are. And the limit will depend on J and K. So at the limit, we expect a object with the two indices. That's the main thing, two indices. So it is actually like that. Measure in the phase space with values in this J and K vary freely 1 to P. So there are, so this is the measure space now. And you have this matrix of H measures. So mu is a matrix now. Mu is a matrix. And it has these properties. So as a matrix is a non-negative definite. So in other words, you take, Chairman, just to hold on. Okay. So you have any test function you take, you multiply and then add with respect to summation with respect to J and K, you get that. Now this is self-adjoint. So this property also holds because it is a question of interchanging these two, the indices of these two. And because of that bar, you get that bar. And this is the non-negativity. Self-adjoint, non-negative definite, if you like. And this is the statement regarding the, so in other words, it's an old story, same compactness holds for the commutator, and you arrive at this combination, and it's the same thing. When J is different from K, you cannot expect non-negativity because this argument, I take phi1 equal to phi2 equal to phi, that fails because we have, here we have the same sequence, U epsilon, and that's why we could write this. If you have U epsilon J, U epsilon K, you cannot do that. So you don't expect, what you can prove is only this. As a matrix is a non-negative definite because there is a summation. Because of the summation, we get back to the same phi, if you like, same U epsilon, if you like. So you have this. So this is a statement for, and now if you go to Patrick Gerard's work, he has extended this to vectors with the infinite number of components and so on. And as a consequence, he gets compactness of velocity averaging and applications to Boltzmann equations. Okay, it's a long story. So it has a lot of implications but for extending this to P equal to infinity case also. Okay, thanks.